All right, good morning, everyone. Welcome. This morning, I'm going to be talking about evolutionary architecture. This is something that I've been talking about over the last few years. My colleague Rebecca Parsons has always also been talking about this, and she's the CTO of ThoughtWorks. She's a PhD in computer science, but she also has some experience in evolutionary biology, so she knows whereof she speaks on this subject. And then my other colleague that's working on this book is Pat Qua, who is an architect and tech lead in the UK. All three of us have been talking about different aspects of evolutionary architecture for the last few years, and so we decided to get together and write a book about it, and this talk is the outcome of us doing some thinking about this topic by way of writing this book, which we're working on right now. And some of this is really just a different perspective on some things that you've seen in software, but we're trying to look at it through a different lens because of some observations that we've made about the software development ecosystem. And it's the first observation is that the software development ecosystem lives in a state of dynamic equilibrium. So everything is cool and stable, and then some new thing comes into the ecosystem that the ecosystem has to respond to, and it finds a new dynamic equilibrium. This is illustrated by this illustration of molecular diffusion. So if you have a bunch of molecules here and then you open up the barrier, those molecules will fill all of that space as much as possible, the same as you saw with that color transition down below. The way that this affects the software development ecosystem is, let's say that you're an enterprise architect, and 2 years ago you made a really nice 5-year plan for what the software development ecosystem at your company is going to look like, and then Docker comes along. And you can take that 5-year plan and wad it up and throw it in the trash can because it makes no sense anymore, because the ecosystem has to respond to this new thing that we've never seen before, and it finds a new balance. This is a problem for software architecture because we like to plan for things, but you can't really plan long-term in this kind of environment. And we don't think this environment is ever going to change because this is just the nature of the way that the software development world works. And so that's why we're thinking about an alternate way of thinking about architecture, this idea of evolutionary architecture. And so here is our working definition that we're working on right now. And in fact, so much so that we changed one of the words since I've had a chance to update my slides here. So I'll give you the new slightly improved definition here. And I'll explain why we changed one of the words in a second. An evolutionary architecture supports continual and incremental change as a first principle along multiple dimensions. The word that we've changed here is continual. We've changed it from continual to guided. And I'll tell you why that is in just a second, because we think incremental implies continual. But I need to explain several of the terms of what I mean in this definition. And let's talk about the dimensions part first. A first principle along multiple dimensions. But first, I need to talk about different types of architecture. Software architecture is not a singular subject. It's really just a perspective on the way you look at a project, because you can look at a project with several different kinds of perspectives. The one that we most commonly talk about as software developers when we talk about architecture is the technical architecture. This is the implementation parts of the architecture. This is the libraries and the frameworks and the transitive dependencies and the integration headaches, and all those things form the technical architecture of your application. But there's also a data architecture, which is the database schemas and the table layout. So some companies have data architects that worry about the long-term structure of how databases fit together. You also have, in many organizations, security architecture. This is the security guidelines and heuristics and how we prevent attacks from happening. And this cuts across the technical architecture and the data architecture, so it's an independent thing. A few years ago, we added another entry onto this list, and that's a domain perspective on architecture. And this really comes from this really influential book that was written by Eric Evans called Domain-Driven Design. And I also point to this really excellent implementation guide, because domain-driven design is a little abstract. Implementing domain-driven design by Vaughn Vernon is also quite good. But Eric Evans, in domain-driven design, it's ostensibly an object modeling technique, but he defines some interesting concepts, and one really influential concept on architects which is this idea of a bounded context. So within the domain-driven design world, once you've identified one of these logical domains, you create around it a bounded context, meaning that within the bounded context, you understand how things are implemented in details like schemas and class hierarchies, but no one outside that bounded context is allowed to know anything about how anything inside the bounded context works. You can still ask the bounded context questions and get answers, but you're not allowed to know any implementation details of the bounded context. This is a logical concept introduced by domain-driven design, but what's happened over the last few years is that you combine this logical concept with the engineering practices and continuous delivery, and you make that bounded context a physical thing. And in fact, that's exactly what the microservice style of architecture has done, is taken that bounded context and made it a physical reality. And I'll talk more about that in just a second. So let's talk for a second about the evolvability of architectures. If you have a software architecture, how evolvable is it? In other words, how easy is it to make small incremental changes to that architecture? And I'll first talk about the classic anti-architecture, or the absence of architecture, which is the big ball of mud architecture. This is from a client project that I worked on. The little tiny dots on the perimeter are classes, and the red lines are the connections between those classes. And the bolder the line, the stronger the connections are. The evolutionary possibilities in this architecture are essentially zero, because everything is coupled to everything else. You can't make a change in this architecture without having some ripple effect to every other part of the architecture, which is why you don't want one of these things, the big ball of mud, which is the classic architecture anti-pattern. But let's look at something a little more common and a little less dire, the traditional layered architecture. We separate responsibilities into layers in things like presentation layer, business layer, persistence, and database layer. And so from an evolution standpoint, we say the dimensions of evolvability here are one. Because notice, one of the reasons we put this architecture in place is to allow us to make changes in one layer without rippling out and touching all the other layers. And so part of the purpose for having architecture to begin with is to enable some degree of evolution so that we can make some changes in our architecture without having to touch every other single thing in our architecture. Now notice there are 4 layers here, and so we have 4 opportunities for evolution in this architecture, but still only one dimension, because we can only evolve along the technical dimension in this architecture. But because we have 4 layers, we have 4 different ways that we can evolve this architecture. And so what that means is, as long as we're changing out some sort of technical layer, like the persistence layer, we want to change from Hibernate to Ibatis, for example, that has very little ripple effect because we're really just affecting the technical architecture. One common pattern in the layered architecture is to have each of these layers be closed. And what I mean by that is that when requests come into this architecture, they must go from the top to the bottom and go through each and every one of those layers. This is one of the benefits of having a layered architecture, is that you know exactly what the path of requests are. But this is also a common scenario. Let's say that you add a services layer, and now you still have a closed architecture, meaning every request has to go through that services layer. But some of you suffer from this particular anti-pattern. So see if this sounds familiar to you. You have a layer in your architecture that all it really does is take in input from the layer above and then transform it into some other data format and then transfer it to the layer below. It doesn't actually do anything to it. It basically just passes it through the layer to get to the one below. How many of you have an architecture like that? I bet a bunch of you do. This is the common anti-pattern called the architecture sinkhole anti-pattern. It's when you have a layer there that you're forced to go through, but it's not really adding any value. And so one common solution to that problem is to make the optional layer an open layer, meaning that you can skip it if you need to. So now you can make a call directly from the business layer to the persistence layer, or if it adds value, you can make that call through the services layer as well. And while this solves the architecture sinkhole anti-pattern, it cuts down on our opportunities for evolution. because now we've introduced extra coupling. Because the business layer is now coupled to the persistence layer as well as the services layer. So if I make a change to the persistence layer now, I'm going to have a much bigger ripple effect, and it's going to be harder to evolve one of those particular layers. And so my dimensions for evolution are still 1 here, but my opportunities for evolution have actually gone down because I've increased the coupling between those layers. Keep that in mind, because it turns out that the way things are coupled together in architectures turns out to be one of the really crucial aspects of building an evolutionary architecture. But let's look at a different architectural pattern, microkernel. This is a really common architectural pattern for things like browsers or build tools, or for example, Eclipse is a good example of a plugin architecture. Again, we have 1 dimension of evolution here. You can evolve the behavior by making new plugins and giving it new capabilities, but that's the only dimension of evolution that you really have inherent in this architecture. Now, it doesn't have to just be in technical architecture that you talk about dimensions of evolvability, because think for a moment about REST plus HADIOS. Hypermedia is the engine of application state. This is the level 3 ultimate conclusion if you get into the REST kind of architectural style. And the idea here is that when you make a request for some resource, part of what you get back from that request is a set of links that are in the next step in that business process. So you follow one of those links, which gets you a resource, which includes links to the next step in the business process. So what this allows you to do is modify a business process by changing the links you send to a consumer without notifying the consumer that you've made any changes to that workflow. And so this is really a kind of a workflow perspective on architecture, because you can implement this on all sorts of different kinds of technical architecture, but this is really a kind of a workflow architecture. But again, the opportunities for evolution here, even though it's not tied to the technical architecture, is still just along this workflow. In other words, you can change what hyperlinks get sent back and what those resolve to, but that's really your only dimension of evolution. As I mentioned before, increasingly we've taken a domain-centric perspective on architecture. And when you look at the layered architecture, where does customer live in the layered architecture? If you take a domain perspective on layered architecture, customer is kind of smeared out across the architecture, because part of customer lives in presentation and part lives in business and persistence and database. And so from a domain perspective, this architecture has 0 dimensions of evolution, meaning that I can't make a simple change to the domain without touching lots of different parts of the architecture, because we haven't built the architecture around that perspective, which is exactly what microservices did. In the microservice architecture, the goal here is to create each one of your microservices as its own bounded context. And so each of these services completely isolate the technical architecture inside the service as part of that bounded context, which means the opportunities for evolution in this architecture are n, where n is the number of microservices. Because there's no coupling between the implementation details of these services, you're free to change any one of them in any direction that you want, which means that you have a very evolutionary architecture. And it's really because we've isolated all the coupling inside this bounded context, including dependent things like databases and search engines, etc. And so this is a really good example of an evolutionary architecture. This is one that supports evolutionary change along multiple dimensions. Because if you try to say the definition here is just a single dimension, well, pretty much every architecture supports evolution along at least a single dimension. That's part of the purpose of the architecture. What we're interested in is this family of architectures that allow you to evolve along multiple dimensions, because that's really what we need to try to combat this dynamic equilibrium problem. So that is the multiple dimensions part of my definition. Let's now talk about the continual and incremental change part. So it's very common in these kinds of architectures to decouple deployment from feature release. This is one of those things that's kind of accidentally gotten coupled together in a lot of companies, that when you deploy something into your ecosystem, you also release it to your users. But it's quite common in the continuous delivery world to use mechanisms like feature toggles so that you can deploy a component without impacting the user and then turn those features on independently of deployment later. And so it's quite common in this world where components are deployed into the ecosystem, but they don't impact our users yet because our features are turned off inside. At some point later, you can decide to actually release those features into a production-like environment, but the only time that it really impacts your users is when that service is actually routed to. And so in this kind of ecosystem, applications really consists of what services are you routing to, which family of services is handling this request. And so let's talk about incremental change. Let's say that you run Widget Co., which is a company that sells widgets, and we have a widget catalog, we have salespeople, etc. And there is a service running in our architecture for star rating things in our catalog, customer service, satisfaction. You can give them a star rating. So a bunch of people use the star rating service. And then at one point, they release into the ecosystem a better star rating service that allows you to do half-star ratings. So you could rate something 4.5 stars and not just 4 stars. And they release it out into the world and make it available to these other services. And the other services, in their own time, as they want this new capability, start gradually routing toward the new half-star service. And over time, everybody migrates over to the half-star service and no one's using the star service anymore. It's quite common in these kinds of architectures that you monitor not just the services, but also who's routing to those services. And if you have a service that no one is routing to anymore, you garbage collect that service out of your architecture. This is what we mean by continual change, the ability to put something live in your ecosystem, to allow other people to evolve to it at their own pace, at the time that they want to, and still support the old behavior as long as we need to, and then let that fade away once we can verify operationally that no one is using that service anymore. And so that is continual and incremental change as a first principle along multiple definitions. That's our definition. Now, the word I changed here, the word we changed, I just met with Rebecca in Chicago last week, is we've changed continual and incremental. We've gotten rid of continual because that's not, you don't have to be continual, and added guided, which is fitness functions, which I'll talk about in just a second. And so that now finally brings me to the agenda for this talk, the first part of which is the definition, which I've just gone through. Now I'm going to talk about a bunch of characteristics of this family of evolutionary architectures. I'll talk about some of the principles that you can utilize to get to one of these evolutionary architectures, and finally some engineering practices that make these things possible, because one of the interesting characteristics of these architectures is almost all of them that we've identified so far fully embrace operations and DevOps as part of the architecture, and that's part of this superpower that these architectures provide. And then finally, a little glimpse of, once you've adopted a bunch of these practices, a way you can fundamentally change the way you think about building software. And so let's first talk about some characteristics and some lessons that we've learned over the last few years, particularly because of continuous delivery and the DevOps revolution, etc. Sometimes as architects, we have well-meaning but incorrect instincts for things. And one of our instincts is to build single sources of truth for things, because duplication is clearly bad, and having a single source of something is good, because there's no ambiguity there. And so a lot of architecture spend a lot of time trying to build these canonical representations of things. And we have a client who did that in a traditional kind of service-oriented architecture. They are an airline, and their architects built one of these really hugely scalable service-oriented architectures, and they got together, and everything they know about customer, they embodied inside this giant customer service. And then a volcano exploded in Iceland. And pretty much everyone who had a ticket on that airline called their customer service desk to say, hey, is this volcano going to affect the flight that I have on your airline? And people in other parts of the world who had nothing to do with this volcano couldn't board their airplane because boarding an airplane requires a customer lookup. Customer service calls require a customer lookup. Changing tickets, which they're doing a lot of, requires a customer lookup. And because customer rules everything in the universe, it became this giant bottleneck. Now, what would have happened if they had built an architecture where boarding the plane only knew enough about customers to board a plane, customer service could only read enough about customers to interact with them? They would have had probably some code duplication here and there. They might have even had data duplication somewhere about customers, but they would have survived this admittedly unexpected but very real world kind of storm. And what this really taught us as architects is that architecture is really abstract until you operationalize it. Let me explain what I mean by that. As architects, we're really good at drawing these lines and boxes drawings of architecture. And this is a valuable thing because we need to understand the topology of how the pieces fit together in our architecture. But a lot of architects think that this is good enough. This two-dimensional representation of architecture is all that you need to do, and they spend most of their day drawing prettier and prettier versions of this in tools like Visio and OmniGraffle and drawing tools like that. But what continuous delivery has taught us is that this is really only the first step in architecture. Because once you've figured this out, now you have to flesh out the 2 dimensions into actual 3 dimensions. And so the box that's labeled ORM, you have to assign that to an actual piece of software with a version number and with dependencies and make it work within the ecosystem that you've got set up. This is a 3-dimensional view of architecture, one that has been hydrated and you can prove really works in a realistic operations center. But this is not enough either because of the dynamic equilibrium problem that I talked about before. We always have to expect change. Even if something like Docker doesn't come along, you know that in 6 months, Hibernate is going to rev its version number, and you need to find a way to still support that new version of Hibernate in this new architecture. This is a 4-dimensional view of architecture. And in fact, we know we're going to have to carry this on into the future. This is a modern perspective on architecture that really architecture is not just lines and boxes, it's really the responsibility of getting it live and keeping it live and healthy over time, which is a larger responsibility. In fact, this is another characteristic of this, that the role of architect has expanded somewhat. Because back in the pre-continuous delivery days, in these typical siloed kind of organizations, you had engineers and architects working together, but then DBAs live in another walled-off silo and operations in another walled-off silo. But to enable this kind of continuous processing and evolutionary architectures, you have to incorporate all of them into the same feedback loop. And so the role of architect now has become a lot more central to this because in many cases, only the architect has the correct perspective across all those silos. Now, this doesn't mean, as convenient as this would be, that the architects are now the king of the world and get to boss people around, because very often you don't have that ability in your organization. What this means is you have to become much more collaborative with the other leaders of those other silos to be able to coordinate things like continuous deployment and evolutionary architecture. Another really common characteristic of this style of architecture is decentralized data management. When you have monolithic applications, you have a monolithic database, it's very easy to wrap big things in transactions and to build transactional behavior into your application architecture. But when you get to things like microservices, for example, that bounded context is meant to encompass things like databases as well. It's literally every dependent thing for that service should be part of that bounded context. And so each of these services is expected to maintain its own database, including its schema and the migrations and operational things like backups, etc. But that means that things like transactions are much more difficult in this world because now you're talking about distributed transactions. And so a really common characteristic of these kind of architectures is they tend to be eventual consistency architectures rather than ACID transactional architectures. And let's talk about that for just a second. We're all super familiar, of course, with the acid characteristics of transactions: atomic, consistent, isolated, and durable. But there are a whole family of alternatives to this, usually playing off the ACID acronym, like BASE, which is basic availability, soft state, and eventual consistency. Even if you're not making big architectural changes, a lot of people end up in this eventual consistency kind of world, because it turns out that as you have to support larger and larger numbers of users, which forces you to physically partition your data across more and more kind of physical nodes, at some point you get to the place where you can no longer guarantee the ACID characteristics of traditional transactions because of the CAP theorem. Once you reach a certain level of physical distribution, you can't guarantee ACID principles anyway, and so this is why a lot of giant companies go to eventual consistency instead of transactions, because it's just a lot simpler. But this is, I think, a disservice that we've done to our users, because we've made our users think that transactions are a natural part of the universe, and they're really not. One of my colleagues several years ago famously made the observation that your favorite coffee shop does not do a two-phase commit. Because when you order your coffee, you may get some sort of little receipt token thing, but then you have to go to another part of the shop to actually get your coffee. Now, what would a proper two-phase commit in a coffee shop look like? You'd hand them their money and you'd get your coffee and you'd let go at the same time. So that's a proper two-phase commit in a coffee shop. So why doesn't your coffee shop do that? Wouldn't it make you feel more secure as a coffee member buying at the public if you got a proper two-phase commit? The reason they don't do that is because it's really, really inefficient to do that. They'd much rather batch those operations up. Everyone's favorite example of transactions are banks, but no teller machine in the world does what we call a two-phase commit for two reasons. One of which is they're all designed to work in case their connection to the mothership gets broken. They can still give money out and then audit and reconcile. But the other more pragmatic reason is that no one wants to stand at a teller machine for 8 or 10 minutes while some mainframe record somewhere in a bank is queried to find out what your transaction is, and tying it together with all the other transactions that you might be involved in. You know, banks existed before computers existed, and bank records used to travel on horseback, and there is no two-phase commit when there's a pony involved. So we have to get away from telling our users that the universe is a transactional place, because there are actually very few examples of real transactional kind of behavior out in the world. Having said that, there are still some circumstances where you have to do transactional-like things. If you're giving away seats on an airline and there are only a few left, you have to treat that transactionally. And so the advice from the microservices world, this is from my colleague Sam Newman, is to try to avoid distributed transactions if at all possible. But you'll notice even in a lot of the diagrams you see for microservices, you'll see instances where they have violated this rule because it's just too hard to break apart a transactional context. So they cheat a little bit on the purity of this rule. I kind of equate this to, so many of you are familiar with relational database theory. You know, you can go to 7 normal forms in relational database theory. How many of you have gone all the way to 7 normal forms in your database? It's okay, you can raise your hand, you're amongst friends here. Yeah, I notice that no one has really done that. You get to about 3rd normal form and you go, you know, this is good enough, because it gets a little crazy once past here. And a lot of that same pragmatism rules here too. What this really is to an encouragement to think about limiting the scope of transactional things as much as possible. And the real reason you want to do that is because transactions form a unique, different kind of coupling. Normally, when we think about architectural coupling, we think about the structural coupling of how classes fit together. Transactions are an example of temporal coupling, because these things are coupled together in time. And that's a really tricky thing to pull apart. And so one of the tricky things that many of you discover if you're going from a monolith to microservices is the trickiest thing is managing those transactional contexts. And so you try to avoid that as much as you can. Another side effect, though, of this kind of architectures is decentralized governance. So let's say that you're one of these, building one of these services, and which is another Another common pattern here is to have a cross-functional team, which I'll talk about in just a minute, building these services, meaning that you have an operations person, a DBA, and developers, and basically everything you need to make this work. And another common characteristic is that your team is responsible for every aspect of this, including putting it live, including things like provisioning database servers. It's part of your responsibility because it's in your bounded context. And let's say that you're running the star rating service and you need a database, but you really just are never going to have more than a few hundred records. You don't need to do any kind of sophisticated querying or anything like that. And you've also made the observation that, I can take a Puppet or Chef script and get MongoDB running in about 2 minutes flat, and I'm pretty sure the first Oracle install dialog won't come up in just 2 minutes. And so you may decide, we're going to use something really simple here like Mongo. And then 6 months later, you realize, that was a disaster. We never should have used that. We should use Postgres instead. So you throw that away and use Postgres, and nobody else cares. Because no one knows what's going on inside your bounded context. That frees you to make implementation decisions that make the most sense for your architecture. Now, this is not an excuse to go off and have every single software team have their own magical software stack that only they understand. But what we're trying to do is get away from this kind of one-size-fits-all that is very common in monolithic architectures. Because when you have a monolithic architecture, governance is really tricky. Because when you're picking something like persistence framework, everybody is going to be affected by this because you're all inside a monolithic architecture. When you choose things like database, everybody is affected by that. And so the side effect of that is you're using some sort of industrial strength database for everything. Maybe 20% of your applications really need that industrial strength power, but because everybody has to share everything, every team takes on the full complexity of the most complex thing, even if they don't need to. And so one of the nice things in this world, by decoupling all of these services from one another, by having no shared technical architecture at all, that frees up the teams to try to pick the right size technology stack for the problem they're trying to solve. You don't need an Oracle database for every single problem. In fact, when you start thinking about it, a very small subset of your problems probably need that much industrial strength, and you're paying a huge complexity tax for having it on much smaller things. And so this actually makes enterprise architecture much easier because it allows you to right size the technology stack for the problem that you're trying to solve with that particular service. As I said before, the main characteristic of these evolutionary architectures is coupling. Whether it's structural coupling or temporal coupling, this is the thing that makes it hard to evolve architectures. So one of the things that we're anticipating is that we may end up writing 80,000 words and end up with a 3-word summary for our book, inappropriate coupling bad. But we think there's going to be a little bit more than that. But it turns out that as you start thinking about the evolvability of architectures, the way things are coupled to one another comes up over and over and over again. So those are a bunch of characteristics of these kind of architectures. Let's talk about some principles by which you get to those kind of architectures. Because we can't really lay out a plan for building these kind of architectures, but what we can do is to elucidate, to call out some principles as to how you get there. And there are a bunch of these. I'll just touch on each of these. We have lots of examples of all these in our book, but I'll touch on a bunch of these. And then one of these first principles is around the nature of architecture. And I'll start this section with the poetry of Donald Rumsfeld, who very famously said, "There are known unknowns." That is to say, there are things we now know we don't know, but there are also unknown unknowns. There are things we do not know we don't know. And he didn't realize it at the time, but he was really talking about software architecture when he made that quote. Because this is the thing that really nabs software architecture. It's the unknown unknowns. It's not the known unknowns. Let's say you're building a new application and you need to do geolocation, and you've never done geolocation before, but you know that you can go learn about that and find out, so you can build time into your schedule for geolocation. It's the unknown unknowns that always nab you. It's the stuff you didn't know that you had to go find out about. And so Docker is a great example of an unknown unknown, that when you start on some project, all of a sudden this new thing comes into the world. There's no possible way you could have made a plan that would incorporate the existence of containerization before that was a thing out in the world. And so one of the principles that we have built around this is this idea of trying to be pro and reactive versus predictive. Because what traditional architectures have tried to do is predict the future. And it turns out that crystal balls are terrible at predicting the future because they can't accommodate this dynamic equilibrium. And so we prefer to be pro and reactive. And let me show you what I mean by that with a case study. Being proactive means building architectural components with the realization that we'll probably need to change them later and be able to react and change those without too much pain. So here's an example. This is a project that I worked on on and off for several years. This is a Ruby on Rails project, and I'm interested here in the evolution of how asynchronous messaging came to work in this application. Very early in this application, so this was the application it was called OVE.com. It's basically autotrader.com for used car dealers. So if you're a used car dealer, you can get access to this site and then buy and sell used cars online at wholesale. Oh, it turns out that the common usage for this application, I don't know if this is true here, but I suspect that it is. In the US, people don't trust used car dealers. And it turns out that other used car dealers really don't trust used car dealers. And so they wanted like 50 pictures per car. They basically want every molecule of the car before they're going to buy it online. And so the common usage was these huge batches of photos. And no one wants to stare at an Ajax spinner for an hour. And so they wanted progress bars, a sense of progress that, you can start a job and come back or get some sort of sense of progress. The traditional way that you do this, of course, is with an asynchronous message queue. And we thought about that, but we also found through a little research this little thing called background RB, this tiny little thing that simulated a message queue backed by a relational database, and we deemed that good enough for the problem at hand. But we also knew that this problem may get more acute over time, and so we built it behind the equivalent of a Ruby interface. At about the 2-year mark, about the 1-year mark, a second request came in for asynchronous behavior, timed events for things like sales and other sorts of anticipated events. We thought about adding a message queue, but then realized that we could create another instance of background RB, and it seemed to work just fine. At about the 2-year mark, a third request came in for asynchronous behavior like updating queues and caches and counts and things like that. And at this time, we realized that the asynchronous behavior of this application was becoming an important part of its behavior. And so at this point, we decided to go pick a real message queue to handle this problem. So we picked this very lightweight message queue in the Ruby on Rails world called Starling. And it took one pair of developers less than a week to switch out the old background RB infrastructure for Starling. Because we'd built it behind an interface, all they really had to do was change stuff behind the interface without impacting other people's ability to work on that project. What was nice about that was one common anti-pattern that we see a lot is that as soon as you encounter some sort of thing like, oh, we need asynchronous messaging, one instinct is, well, let's go buy the fanciest, most complicated one we can, and we'll grow into it as we need more capabilities over time. The problem, though, is that those really expensive, fancy ones have a lot of features you don't need now, which really just manifests as technical debt. So what we'd rather be able to do is put the simplest thing that will work right now in place, as long as we don't have to pay a big penalty for swapping it out for something more capable later. That's what I mean by being pro and reactive. Try to always balance the needs against the technology you're using, but don't back yourself into a corner. Make it so that you can swap yourself out easily later. And in fact, that goes around to the first process example that I have here, which is this idea of last responsible moment. This is something that came to us from the XP guys. They talk about last responsible moment. This is common in the architecture world. And the idea here is that for any component of your architecture, you'd really like to delay decisions about it until the last responsible moment. Not the last moment, which means it's too late to be effective about it, but try to delay it to the last responsible moment. And one of the ways to determine that is look at the load that this particular component is undergoing, what kind of job that it's doing. Is it taking on new responsibilities or new levels of scale that it need to before? Maybe that is the time to evaluate, should this part be replaced or not? And a really common pattern to guard against this is one that I mentioned before. And this is actually advice from the domain-driven design guys. Anytime you're wiring your application to some sort of external API, like geocoding or some sort of specialized behavior, rather than wire yourself directly to it, wire yourself instead to an interface so that when it comes time to change out this capability in the back end, hopefully most of the change will happen behind this interface and won't affect the rest of your application. This is what domain-driven design calls an anti-corruption layer for your application. Don't corrupt your API with someone else's API, and this actually makes it easier to be pro and reactive when you change things. This is not an excuse to abstract all the things. Some of you will take this advice to say we should build interfaces around interfaces around interfaces around interfaces so that we have indirection everywhere. Tooling today means you don't have to proactively do this. Once you find a place that you need to wrap it in an interface, you can right-click and say extract interface and move on at that point without doing it up front. That's what we mean by pro and reactive. Another common characteristic, another principle in these architectures is try to bring the pain forward. This was something that the extreme programming guys realized when they started thinking about continuous integration, because a really common pattern in the 70s and 80s and the early 90s, in fact some companies still do this, is to have a bunch of people work on code independently, and at the very end of the project there's this big integration phase where they integrate all that code together and actually make an application out of it. The extreme programming guys in the early 90s were a group of developers who had collectively worked on several hundred projects. And they were depressed at how software development was going because it seemed like no process that you picked was a good predictor of project success. And so what they did was kind of throw away all the processes that existed at the time and try to build this practice around things that they know have worked well in the past. So they know that testing has yielded better code bases. And so what's the most extreme version of testing? We'll write tests before we write code. That's test-driven development. And one of the things that they invented was this idea of continuous integration. Because they'd been on projects like this before and realized that that last painful integration phase was something to be avoided, and they invented this idea of continuous integration. What's the most extreme version of that? Well, let's make sure that everyone incorporates their changes all the time, every day. That's this idea of continuous integration, and it was really the underlying principle behind that was bring the pain forward. Anything that you can identify that's really painful from an engineering practices standpoint, that's very cumbersome, it takes a long time, a lot of manual steps, etc., their advice is to bring the pain forward, meaning force yourself to do that more often, and you'll force yourself to automate it away, and then it just kind of evaporates. And that's exactly how we ended up with continuous integration. Because what they stumbled onto is this really interesting observation about many of the engineering practices in software. Things like merge conflicts and anything that has to do with the kind of way things are coupled together. It seems like as your code base gets slightly bigger over time and as time goes by, that things should get linearly worse over time. This just seems natural. But a lot of things in software don't act like this. They act more like this, that they get exponentially worse over time. And you all have felt this with merge conflicts. Because if you check something out and you check it back in a few hours, you get very few pain. The longer you leave that out, the worse that pain is going to get. It's going to get exponentially worse, not linearly worse. Lots of things in software work like this. This is part of the motivation for the XP guys to say bring the pain forward. Anytime you identify some of that pain, try to push it further forward, and you'll end up eliminating by automating away. And in fact, this is one of the underlying principles behind all of the continuous delivery stuff, is find ways to automate and bring pain forward. You see lots of examples of this in continuous delivery. This is exactly the role of deployment pipelines in the continuous delivery world, because now go back to that continual example that I gave you before. That presumes continuous deployment. But notice that continuous deployment is not nearly as scary anymore when deploying a component doesn't mean you're releasing something that your users are going to have to deal with. Continuous deployment really just means get it into the ecosystem to make sure it plays nice with everybody else. It doesn't take up too much memory or eat up resources. It monitors and logs correctly and all that other stuff. You can turn on features later. But if you're in a continuous deployment kind of world, a really common scenario is, okay, I have my current production set of services and I'm making changes to some other services that are going to be the next release. I want to be able to continuously deploy all these things, and so as soon as I make a change to this service, I want to make sure that it works against the current production stack and the new head of my version control. That's what's called a fan out in a deployment pipeline. As soon as you check that in, the deployment pipeline fans out and runs tests in parallel in both environments, and if both are successful, then it fans back in and deploys that component into the ecosystem. This is true in the advice to do database migrations and refactoring. Databases are not immune to all this evolutionary stuff. We have to have an evolutionary approach to those as well. And continuous delivery talks about migrations and refactoring as a way to do that. And really any kind of automation in the software world is an example, in many cases, of this idea of bringing pain forward. Let's talk about some people stuff. This is really what Pat is focusing on a lot in this book, but this is really critical because you can't really affect architecture without affecting the people who build that architecture. That's really an observation by Melvin Conway that has come to be known as Conway's Law. This is an observation Melvin Conway made back in 1968, that organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. This is becoming a really common trope. I'm looking for a better word than that because that's an obscure English word. A very commonly quoted phrase in the microservices world. So O'Reilly, the publisher, had their first software architecture conference in Boston last March. And I was on the program committee, so I got to see all the abstracts. About 80% of the abstracts were about microservices in one form or another, and only 50% of the conference talks were about that. So we didn't get the proportion of papers to conference subjects, because we didn't want it to be solely about microservices. But during the conference, it became almost an in-conference drinking game that every talk would mention Conway's Law at one point or another. So it became known that as soon as this talk mentioned Conway's Law, you could take a drink and move on. Because every talk mentioned this. And really what this is the observation that the way that you organize people ends up affecting the way that the things that they build get organized. And the way this affects software projects is, let's say that you have a bunch of UI specialists and a bunch of middleware specialists and a bunch of DBAs running around. You will probably produce an architecture that looks like the communication structures you have in place. It's just easier to build something that maps one-to-one like that. But when you take on a more domain-centric view of the world, that means that you need to split up your teams in a similar way. And so rather than splitting out your teams by role, the suggestion in this world is to split them into cross-functional teams around domains instead. We're building more and more domain-centric architectures, and so why not build teams that look like the architectures you want? We call this two different terms. This is the inverse Conway maneuver. It's the realization that Conway's Law is going to affect your project whether you want it to or not. So why not use it as an advantage rather than something you have to fight? Actually leverage Conway's Law. If you're talking to an enterprise architect, though, and really want to impress them about this concept, you should refer to it as domain architecture isomorphism. Mapping the architecture to the domain, which sounds a lot more official, but it means the exact same thing. Really what this is this idea of building these cross-functional teams organized around business capabilities that look like the target architecture you want, and it's going to be easier to achieve that architecture because Conway's Law is going to affect your project whether you really want it to or not. And this, again, is just another example of domain-driven design's physical context, physically realized, both with architecture but also teams. Another perspective of this world is products rather than projects. So when you think about most software projects in large organizations, a bunch of developers get together, they hit a release date and then hand it off to someone in operations, and then they move on to some other project. This person in operations has to do the care and feeding for this thing for the rest of its life. Product-centric approaches have a different way of attacking things. Amazon is very commonly kind of pioneered this idea. At Amazon, they have what are called 2 pizza teams. No software development team shall be larger and can be fed with 2 large pizzas, which is 10 or 12 people per team, and they're cross-functional, meaning they have developers, they have business analysts, they have a DBA, they have an operations person on their team, because they're responsible for putting it into production, and they're responsible for operationalizing that service that they own. The side effect of this is that you have product owners that own this service and act within the ecosystem to find new uses for these products. And you have a much stronger engagement of people on these product teams because you're all working together as a team. When you need some sort of operational support, you don't have to call someone in another silo for some person that you meet once a year at the Christmas party. It's someone on your team that is empowered to do that, and it removes a tremendous amount of friction when you do that. So the last of these principles that I want to talk about are fitness functions. And this is the important new word that we've added to this definition, this idea of guided evolution. And the way that we do that is with fitness function. So we're talking about an evolutionary architecture here, which implies one that changes over time incrementally. But we want to guide that change. And that's this idea of a fitness function. And fitness functions can be either things like metrics or they can be tests. So for example, maybe one of our fitness functions says we want to ensure that we always have a certain page load time. So let's say 1 second load time for pages is the service level agreement that we're interested in. That's a fitness function, so we'll build a test very early on that all it does is verify the page load speed for every page that we build. So that as soon as we violate that fitness function, we have a failed test and we can investigate it right away. We don't find out about it much later. But it also could be metrics. So maybe another example of a fitness function is the really common metric in continuous delivery is cycle time. How long does it take to move something from development into production? And you want to keep cycle time really short, you might have a fitness function that says, no matter what we do, don't let our cycle time grow more than 6 hours. And so that's one of the fitness functions for your project. We want this guided behavior in our architectures because we're talking about evolutionary architectures here, but if we really modeled architecture the way evolution works, what we do is build an architecture that just makes a random change every once in a while, and we might have a killer architecture in a few million years. We don't have a few million years to wait to get a better architecture. That's why we want a guided architecture. So we're building dog breeds here. We're guiding the evolution of our architecture because we'd rather have a dog breed and not a platypus. So we're not trying to create architectural platypi here. We're trying to create a guided evolution through these fitness functions. And the other observation is that these will definitely grow and change over time. As you get deeper and deeper into your project, you're going to change the values of those metrics. You're going to pick up new fitness functions along the way. So the anticipation here is that these are a living part of your project, not something that you kind of latched onto midstream. And finally, a few anti-principles, things that make evolutionary architectures really hard. Heavily transactional systems don't fit well here. So for example, microservices is not a good architectural match if you have a really heavily transactional system because transactions are tough in microservice architectures. You're actually better off in a service-based architecture rather than a microservice architecture if you're going to do a heavily transactional system. Certainly, if you have a lot of out-of-control coupling, you're going to have a hard time with an evolutionary architecture. Coding via configuration for things like enterprise service buses or business rules engines or anything separate to the technical architecture, it's hard because now that's an extra coupling point that's not really part of the technical architecture. It's another dimension of coupling. And really restrictive governance is also makes evolutionary architectures hard because you're trying to do a one-size-fits-all approach to everything. So let me touch on a few of these practices. I've alluded to several times here the practices in continuous delivery, which are really important to make these kind of architectures work. One of the things that we say is you must be this tall to use microservices, meaning that if you don't at least get to this bar, then you're probably going to have a really bad time. A really common practice in continuous delivery are things like feature toggles, which I alluded to before. Instead of doing branching to handle things like in-flight features, instead add configuration to your application. So these are toggles that you add at all the different parts of your application so you can toggle behavior on and off. This is a really common practice. In fact, there's a really great article series that just appeared on martinfowler.com about feature toggles and all sorts of scenarios and uses for them, which we find quite nice. Deployment pipelines are another common characteristic in this world. For engineering practices, you need the ability to integrate things automatically using tools like deployment pipelines. This is GoCD, which is an open source deployment pipeline. It's taking 3 different projects and making sure that they're integrated together by doing testing on them, and doing fan in and fan out and other sorts of behaviors like that. The team practices I mentioned before, having really good cross-functional teams makes a big difference here. With articulated principles, not so much coding guidelines necessarily, but the way that the architecture is supposed to work, written down as principles. We're also big fans of spreading architectural knowledge around on the team. There's this idea of architectural briefings that when you make an important architectural decision on your project, have a meeting, a brown bag lunch, and discuss that with the rest of the team to give them exposure to that, the thinking that went behind that. One of the really tricky things about architecture is how do you get better at anything in life? You practice it. Well, how often do you get to practice architecture stuff? Not much. And so every opportunity you have to practice architectural thinking with your whole team, you should take advantage of that. What we're really looking for here, so a side effect of a bunch of these things that I've talked about are experimentation enablers. Things like feature toggles, things like having spikes, time box experimental coding exercises, having some trusted users you can guinea pig and try some things out on, and having really good metrics and fitness functions allow you to play experiments, which leads you to a completely different style of development. And it's this idea of hypothesis-driven development. There's a great podcast called Radiolab. It's not about technology, it's just about really interesting stories. In 200 years, when they point back to the origin of podcasts as literature, Radiolab is going to be one of their best examples of this. And Radiolab tells a really interesting story. It's the episode called The Trust Engineers. This is back in 2013, but Christmas 2013 to New Year's Day 2014. Facebook had more photos uploaded to them than all of Instagram. And they had a really serious problem because over 1 million photos were flagged as offensive. And they are supposed to go through every one of those and determine are they offensive or not, and they don't have enough staff to do 1 million photos. But then they started looking at the photos, and it was things like puppies and guitars and people standing on the beach. It's like, what's offensive about this? And so they started asking their users questions. And they started doing this as an experiment. Facebook continuously runs experiments on their users all the time by putting out A/B testing under feature toggles. They were talking to one of the Facebook engineers, and they said that they commonly have more than a dozen experiments running at any given time. And the interviewer said, as a Facebook user, what are the chances I've been in one of the experiments? And he said, 100%. You're probably in 3 right now. And one of the experiments they ran was, why are they flagging this as offensive? And so instead of just offensive, they started asking them a little more multiple choice questions. And they found out the puppy was there because it was because of divorce. And one spouse got the puppy and it offended the other spouse, so they flagged as offensive. They also discovered that people would flag photos as offensive if they thought it wasn't a good photo of them. And so they started asking the question, is this a bad photo of you, or do you look bad in this photo? And it's amazing how many people will say, this is a bad photo of me versus I look bad. So all these little subtle things until they got down to a really small number of things that were truly offensive and they could actually deal with it. The enabler for that was this ability to put experiments out in the world and learn things from their users. And that hints to a completely different style of doing software development once you have an evolutionary architecture in place. So you still have vision and business strategy and business goals, and that leads to ideation, sort of like the backlog that you create now, but rather than create story backlogs, what you're encouraged to do is come up with experiments that you want to run. So you build this portfolio of ideas, of experiments that we want to learn more about our users, and you select a few of them and you play them. And it may be this first one has some promise, but you realize that that's not really what they want, and so you pivot and give them what they really want. The famous example of this is that Flickr didn't start out as a photo sharing site. It started out as a trash talking forum between gamers, and so many people ended up sharing photos on it that one day they realized, oh wait, we're a photo sharing site. We're not a gaming trash talking site. And so they built what their users actually wanted. Some of these experiments will seem really promising, but then your users will absolutely flat out reject them, so you can stop working on bad things more quickly. And some of those things are really going to resonate with your users, and they're really going to love them, and so you can double down on those and put more effort into the things that you can prove that your users like better. This gives you an entirely new kind of feedback loop with your users, where if you have the ability to put things into your architecture with very little cost and effort, where it's really easy to do A/B testing against your users, this enables a completely new kind of interaction with your user, where you can build the things that you know that they want, not the things you think they might want, but instead build exactly the things that they want. What you're building right now is a buffet. You're cooking all these dishes and laying them out and hoping that people will come along and get them. What we're switching this to is an a la carte restaurant where people can come in and let you know exactly what they want, and you can build that thing. A lot of this comes back to dynamic equilibrium. We're never going to get away from this problem of dynamic equilibrium because it's not going to be the Docker the next time. It's going to be some new thing. I don't know what it's going to be. If I did, I'd be a millionaire and I'd be in a startup right now. But I know that it's going to happen. And so that's why that's why we think it's important to study this family of architectures and get better at this idea of evolutionary architecture. So that's why we're continuing to work on this book, and we're going to continue releasing stuff as we go, as we learn more stuff about this. That's all the time I have, and I'm encroaching on the break, which is always a bad idea. I'll be here the rest of the day if you want to chat about something. Thanks very much for coming, and hope you enjoyed it. Thanks. Thank you.